going to go just looking at standard one. And that really concentrates on some of the basics, is just that periodic table. If you are able to print out at least one version of the periodic table, please do so, so that you have it available and you can actually use it to take notes on. There's a lot of information at the periodic table that you can just see based on the color coding, especially for the ones that we utilize in class. But there's other things that you can add to it that will help make chemistry a little bit easier for you. I thought I took this out, but apparently I didn't. So, not that you're going to be asked this on an assessment or something, but the first periodic table was actually created by Dmitri Mendeleev, and Mendeleev put his elements in order by atomic mass. He happened to be a chemist, and he was organizing what we would consider flashcards. It was his notes on all of the elements. He was messing with them and noticed that there were patterns in those elements. And then he noticed that when he put them in orders, those patterns are repeated. Now, our current periodic table is not put in order of mass. It's actually put in order of atomic number. So when we say periodic law, the periodic law basically tells us that if the elements are placed in order by atomic number, which is basically by number of protons, we see a repeatable pattern in the properties of the elements. So looking at the periodic tables that are in our Google Classroom, you'll notice that they are color-coded. If you happen to be ever in one of our science labs across the county, you'll notice that most of them have a really great big periodic table on the wall that has similar color coding. So those red symbols, that red is just to let you know that those elements exist as a gas. So room temperature, oxygen, O2 is just floating around as a little gas. The blue ones, and there's only two elements that are blue. One is mercury, and yes, its symbol does not match its name. And the other one is bromine. These are the only two elements who are liquid at room temperature. And black, that's the number that you see most often. That is to indicate that the elements are solid. So the vast majority of the elements in the periodic table are solid at room temperature. If you were to, for example, look at an example of carbon. So there's two versions of solid carbon. You got diamonds, so, you know, things you find in jewelry. And then you've got coal. So think about charcoal briquettes. So things that you would use in a grill, an actual, like, you know, fire grill, not a gas grill. Now, all of the green elements, all of those green elements are those man-made elements. So notice that there are a few man-made elements that are actually below 95. So those are ones that we did produce. They're kind of unusual in the fact that they spread themselves out across the table. But if I were to put this whole thing together, I would notice that almost all of those man-made elements are in that last period of the periodic table. And man-made just means it does not occur in nature. So we look at our periodic table and notice that we have this little pink line. That little staircase line is extremely important to us. And what it does is it divides the different types of elements. So elements can be separated into three different classes. You've got metals, nonmetals, and metalloids. So your metals are the ones that are yellow on my new graphic. They are the ones that are on the left side of that bold line. The only exception, of course, is hydrogen. Hydrogen is on the left of the line, but it's not a metal. Our nonmetals are on the right side of the line. And those nonmetals plus hydrogen are not metals. So in between the two, we have our metalloids. Our metalloids are the elements who live on the stairs. The way I like to say it is they have two sides touching that staircase. There is an exception. Notice that we have one little yellow block over here who has two sides that touches the staircase but is marked as a metal. Well, if you look at that on our real table, you'd see that that is aluminum. And if you've ever seen aluminum foil in the kitchen, you'll notice that it's a solid and it's shiny and it conducts heat. Therefore, it's a metal. It is one of the, again, another exceptions on the periodic table. So when we're looking at our metals, metals all tend to have some of the same properties, some of which I mentioned a moment ago with aluminum. Metals tend to have luster, and what that means is they're just shiny. They tend to be ductile. So ductile means that I can pull them into wires. This is how we're able to make jewelry and electronics, is because we can actually take those metals and pull them into really thin strands. Metals are malleable, which basically just means we can pound them into shapes. This is how we're able to make coins and bring far other useful resources. Metals are typically solid. Really and truly, the only exception is mercury. Metals will always lose electrons. Metals always lose electrons to form cations. That is really, really important to remember throughout this entire course. Our metals form positive ions. So if you don't remember that terminology from physical science, a cat ion is a positive ion. So a really stupid way to remember it is think of the cat ion as an actual, kitty cat, and cat ions are positively perfect. I know, kind of lame, but I like it mainly because I like kitties. So metals are to the left of that solid, bold, red, black line staircase of the periodic table. They make up the vast majority of the elements. So the other side of that line would be my non-metals. Non-metals are quite literally not metals. So their properties are exactly the opposite of a metal. Non-metals tend to be very brittle, which means they break very, very easily. If they happen to be a solid, they're not a very strong solid. They are non-lustrous, which basically just means they're not shiny. They are very poor conductors of heat and electricity. I failed to mention that metals conduct it really, really well. And the vast majority of my non-metals tend to be gases, but those that are a solid tend to be very brittle solid. Non-metals tend to gain electrons to form anions. Again, something important to know is that our non-metals always gain electrons to form an anion. An anion is a negative ion. So if you happen to be really good at English, you might know that that prefix "an" means not. So a not, a negative ion, but I just kind of like to use the word to help me remember it, a negative ion, an ion. I know some students like to say onion. Don't know why, but it helps them remember that, hey, they don't like onions, so anions are negative. And last but not least, our metalloids. So our metalloids live between the metals and the non-metals. They do touch the staircase. They have to have two sides that touch that staircase, with aluminum being an exception. Metalloids have properties in between metals and non-metals, and it can be a little bit temperature dependent. So metals can conduct, metalloids can conduct electricity under certain situations, and then under other situations, they don't conduct electricity very well. So if you were to have a printed periodic table, you could take and color code your elements just to have that visual reminder of who's a metal and who's a non-metal. My metalloids, again, are in the middle. They live on the staircase or below the staircase. So in terms of the information on the periodic table itself, throughout the periodic table, every element has its own little square. And you'll notice this key on our periodic table, kind of in the symbol, lets you know what each part of that element's square tells you. Of course, our atomic number gives us the number of protons. That is something extremely, extremely, extremely important. Atomic number always equals our protons. The reason it always equals our protons is because the protons are the identity of the element. If you know the number of protons, you know the element. All you got to do is count the protons and you look at it on the table, that number. Next, we have our symbol. with our symbols, they always have a set pattern. If it happens to be a two-letter symbol, that first letter is always uppercase, standard uppercase, and that second symbol is always lowercase. Make certain you're using the right size of the letter, because otherwise you might not be saying what you think you're saying. Then we have their name. Many of the symbols in their names seem to match up, but others don't quite as much, and that would be because their symbol or their name is based, well, their symbol is based on their Greek or Latin name, and we speak English, so the symbol does not necessarily match their name. Next, we have our average atomic mass. Our average atomic mass is a weighted average. We'll actually see a little bit later in this unit how to calculate it. And on our periodic table in our Google Classroom, we actually have one other number that's on the bottom of the right-hand side of our periodic table, 2.4. And that little number on the bottom right-hand side is called the electronegativity value. Again, it's kind of on the key. We will deal with electronegativity later. So for now, just kind of ignore that little extra number that you're not used to seeing. So periodic law, I mentioned this earlier. This is one of two major laws that we deal with in chemistry. Periodic law says that if we arrange the elements by atomic number, so by increasing number of protons, we see a repeatable pattern in the properties of the elements, both chemical and physical. Now, when you're looking at that periodic table, the rows, so the things that go across, are called periods. There are 7 periods on the periodic table. The things that go up and down are our columns, and we tend to call them groups or families. And I forgot to say something with our periods. So our periods will actually equal the energy level. If an element is in a particular period, it has that number of energy levels. So for example, carbon is in the second row down. Carbon has 2 energy levels worth of electrons. I'm going to pick on gold again. Gold is 6 periods down. Therefore, it has 6 energy levels worth of electrons. And then you see me keep looking left because I'm looking at my periodic table. So our columns, our groups are known as our families. There are 18 of them, and elements that are in the same family tend to have very, very similar physical and chemical properties. The reason they have very similar chemical properties is because they have the same number of valence electrons. So if you don't remember from physical science, valence electrons are the electrons that are in the outer energy level. So our valence electrons are the electrons that are in the outer energy level. They happen to be the electrons that do all the reacting. That's kind of why we focus on them a lot when we get to bonding. So our groups or our families all have their own individual name. We can identify them by either their name or their number. So I could say group 2, or I could say alkaline earth metals. Either way, you would need to know to look at the second column on the periodic table, which begins with Be, beryllium. So just in case you don't remember your group names, we're going to talk very, very briefly about each of the groups. I would encourage you, again, have a printed periodic table, jot that group name above the row just to kind of have that visual reminder of what each group is called. There are 5 or 6 group names that are not very obvious, and then there are others that kind of make a lot of sense. So our first group, group 1, column 1 on the periodic table, are called alkali metals. They get their name, alkali metals, because they tend to form basic compounds. Alkali means base. They all have one valence electron, and they all form a positive one charge. We will notice a pattern in the charge in the ions that each form. And with the exception of hydrogen, all of them are metals. Group 1 is one of the 2 most reactive groups on the periodic table. Group 1 elements are not found in nature floating around all by them little cells. They are either bonded to something else or bonded to their twin in the case of hydrogen. And as I said a moment ago, they all form a positive one charge. So you might see this in terms of they form a +1 oxidation state. I tend to use the term charge or ion, but oxidation state is also valid. Group 2 is twice as special, so it has 2 parts to its name. It is the alkaline earth metals. So alkaline earth metals, again, they're kind of basic, hence the alkaline. Earth, they are all found primarily in the Earth's crust, and metals because they are metals. Group 2 elements all have 2 valence electrons. And since they have 2 valence electrons, they form a +2 cation. They form a +2 cation. For group 2 elements, they are all metals. So group 2 outlining in a green box, because my groups do not include those bottom 2 rows. Those bottom 2 rows are their own little special groups. All righty, jumping to the middle of the periodic table. That middle part of the periodic table are called our transition metals. My PowerPoint is out of sync, but it will catch back up with me in a second. So these are our transition metals. We will talk about the ions they form in much more detail later in this unit and again in unit 2. And we'll talk more about their valence electrons once we learn a little bit more information about electrons. But just know that transition metals do all kinds of wonkiness. So our transition metals tend to be all metals, and they do include this entire middle block of the table. Those are all transition metals. So group 13 and the next 3 happen to be named after their lead element. So looking at our real periodic table, we can see that lead element is boron. So therefore, it's called the boron family. And the boron family, they have 3 valence electrons, 3 valence electrons. And since they have 3 valence electrons, they all form a +3 ion. The boron family has 1 metalloid, boron, and then the rest are metals. Carbon family is group 14. Group 14 has 4 valence electrons. Are you noticing a pattern with the number of valence electrons? So my valence electrons happens to match the last number of the group number, or the ones digit, if you happen to be a little bit more mathy. My valence electrons, with the exception of transition metals, tends to match the ones digit of the group number. Group 14 has 4 valence electrons. They are halfway to being stable. So an octet, or 8, is stable, which basically means group 14 can actually form either a +4 charge by getting rid of 4 electrons, or they can form a -4 charge by gaining 4 electrons. We will talk about this in more detail later in this unit and a lot in unit 2. But just know that it can be either or. Either way, you're looking at group 14 typically forming charges of 4. So group 14 is the first group where we actually see all 3 types of elements. We have metals, nonmetals, and metalloids. Group 15, nitrogen family. Nitrogen family has 5 valence electrons. Since it has 5 valence electrons, remember our goal is to get to 8. And it is really, really hard to find a home for 5 electrons to drop down. So what group 15 does is it goes out and steals some electrons, and it will always form a -3 charge. Group 15 forms a -3 ion because it gains 3 electrons. It is, again, a mixture of metalloids, metals, and nonmetals. Group 16, this is the last of the ones where the names kind of match the group leader, and that's the oxygen family. Oxygen has 6 valence electrons. It is 2 away from being stable, so we notice that the oxygen family all tends to form -2 charges. And it is, again, a mixture of metals, nonmetals, and metalloids. So there's really only one metal in that family, but, you know, it's there. Might as well think about it. So last two columns, we have group 17. These have a special name. They are called the halogens or the halogens. I say halogens because I'm Southern. Halogens. Halogens are the second of the 2 most reactive groups on the periodic table. So group 1 and group 17, they are both 1 away from being stable. Therefore, they are the most reactive groups on the table, and they will always be found hanging out in compounds or in bonds. They do not like to float around in nature by themselves. Group 17 all have 7 valence electrons. And since they have 7 valence electrons, they tend to form a -1 charge. They go out and steal 1 electron to form a -1 anion. Now, group 17 happens to be all nonmetals. Ooh, we're back to only one type of element. Last but not least, group 18 are our noble gases. They get their name from the fact that they do not interact typically with other elements on the table. They are noble because they don't form bonds. They don't form bonds because they have 8 valence electrons. There is an exception to that. Helium, He, doesn't have 8 valence electrons because it doesn't even have 8 electrons. It actually has 2 valence, but we will see why later. 2 valence is also extremely stable. Group 18 are all nonmetals, and they also happen to all be gases, hence the gas part of the noble gas name. So those are our columns. We do have 2 more group names on our periodic table. Oh, and I don't have our actual one that we use in class in front of me, so I can't remember if this is, oh, good, it's on the next slide. It's actually on the next slide. So last 2 group names, I don't use these a lot, but they're on our table, so you can actually reference them. The next to bottom row is our lanthanide series, and the very, very bottom row is the actinide series. Now, to make our life easier, we actually group groups of elements together and refer to them as one massive group. That is our representative element groups. These are the elements that represent the vast majority of the compounds on the periodic table, and they are basically your tall groups. So groups 1 and 2, and then 13 through 18. These are the things that make the vast majority of the compounds that we see out in nature. Those bottom 2 rows, not only being called lanthanide series and actinide series, but they also have a special name together. Together, they are also called the inner transition metals. The reason they are called the inner transition metals has to do with the fact that if we put the periodic table together the way it's supposed to be, if I were to cut it apart and put those transition metals in where they go, it looks kind of sort of like that. And I think it's going to be flipped on the screen, but whatever. We can see that those bottom 2 rows actually do fit within the periodic table. There we go. And in case you couldn't see the screen earlier, because it's kind of blurry, lanthanide and actinide series. So, kind of summarizing the information that we see on our table. This is a great color-coded at a glance periodic table to have as a resource. It has the group numbers listed at the top with the number of valence electrons above it and the charge that each of the groups tend to form. Not only that, but it has the solid, liquid, and gas coloring for black, blue, and red, and it lets us know our metals and our nonmetals. This is another great resource that kind of summarizes each of the group names and what elements are included in those groups. So notice that even though 69 and 101 are under the oxygen family, they're not part of the oxygen family, for example. So 66 and 98, they're not part of the boron family. They are actually in the lanthanide and actinide series. So pull out a periodic table, pause the video, and see how you can do with a quick self-check. So this is our We Do activity. In a virtual We Do activity, kind of pause it as you go along, answer it yourself, see if you got it right. If you didn't get it right, that would mean you might want to come into the meet or ask in the meet a question or some clarifications because you missed something in the video lesson. So looking at question number 1, I have out my real periodic table as a reference, but we were specifically looking at only the symbols that are on the screen. So those are the only elements we're going to play with. We're kind of ignoring the rest of them. And to make my life a little bit easier, I'm going to number my group numbers. There we go. That way we just have it there. So question number 1 asked me which one of these symbols is in group 2 and the 4th period. So remember, periods are our rows. They go across the periodic table. They are the periods. So my 4th period would mean I am 4 rows down. So 1, 2, 3, 4. These are my periods. So who was in the 4th period and in group 2? Well, there's only one element. It could be, and that would be magnesium, Mg. And it would not be magnesium because Miss Raines can't count. It would be calcium. Bad, Miss Raines. 4th period. Yeah. Okay, we're going to actually slow down and think before we speak. So group 2, it's asking which one of these symbols are our transition metals. Our transition metals are in that middle block of the table. So that middle kind of boxy area on the table are my transition metals, and we only got one in there, and that's OS, which is osmium. No, you're not expected to know the names. You can look at the periodic table and get the names. So number 3, who is in the 3rd period? 3rd period means 3rd row down. Well, we actually have 2. So you could have put magnesium or argon. Number 4 has 4 valence electrons. So remember, our valence electrons are related to my group numbers. I could just count the tall columns to get my valence electrons, which is kind of what I'm writing here in yellow. Probably should have picked a different color because I can't see where my mouse is with yellow. So 4 valence electrons means we are looking at group 14, and the only one in group 14 that is identified would be C, which is carbon. Number 6, my noble gases. Hopefully you have labeled your periodic table and you have labeled that group 18 are your noble gases. Therefore, we must be referring to argon. And of course, I skipped number 5. But noble gases are argons. Back to number 5 are halogens. Halogens are group 17. Therefore, we're looking at just fluorine F. So number 7, who forms a -1 ion? So ladies and gentlemen, you either want to have on your printed periodic table this pattern or you need to memorize the pattern. So we count up with our first several columns. They are +1, +2, +3, and +4 respectively. But group 14 can also start doing our negatives. So group 14 is where we count down. That is why group 14 typically is shown as positive or -4. Once we get past group 14, we are counting down. We form a -3 ion for 15, -2 for 16, -1 for 18, and no -1 for 17, and none for 18. Our noble gases don't form charges. So who has a -1 ion? Well, it's got to be fluorine. It's the only one that is in group 17. So who has 76 protons? 76 protons means we are looking at element number 76 because my atomic number equals my protons. My protons equal my atomic number. The proton is the identity of the element. So who's number 76? Well, that's not labeled, but I can look on my periodic table itself and I can see that 76 is a transition metal, so therefore it's got to be OS. Although I think OS is not actually shown in the right spot anymore. Something shifted, but whatever. So number nine, who forms a positive 1 ion? Positive 1 ions means we are looking at alkali metals. We are looking at group 1. Therefore, the only one who forms a positive 1 ion that we've identified is lithium, Li. And last but definitely not least, who has 8 valence electrons? 8 valence electrons means they have that octet. An octet means we are our noble gases. So my noble gas who is identified on the image would be argon. Ignore the math. I don't know why I have that. Oh, I know I have that there. So that is it for our We Do activity, how to do. So if you got at least 70, 80% of them correct, you are good to move on to the practice for the day. If you did not get at least 70 or 80% of them correct, go back, rewatch the video, take some better notes, because this is some of the foundation that we will use the entire semester. This is the bare bones basics that you need to build upon for the rest of the course. Hope you have a fabulous day. And as always, I'm available in the Meet for questions or clarifications. That is why I am here. So please don't be afraid to ask. I promise I don't bite, I just nibble.